Bem-vindos. Hoje temos a grande honra e prazer de ter um palestrante um pouco da fora, Đàm Thanh Sơn, da Universidade de Chicago. Ele é originariamente do Vietnã, estudou em Moscou com, infelizmente, falecido recentemente Rubakov. E depois teve diferentes posições na Universidade de Columbia, Seattle, agora está professor em Chicago. Ele obteve muitos resultados bastante famosos na física de partículas e mecânica estatistical, QSS bound, da viscosidade mais baixa possível em qualquer sistema físico, um dos S's dele. Ele foi um dos inventores do transporte anômalo, da consequência da teoria do transporte da consequência da teoria do transporte de anomalias quânticas. E agora ele estuda métodos de física de partículas aplicados à matéria condensada. E também na física da baixa energia, na física nuclear. Hoje ele vai falar isso.
Thank you very much, Dr. for nice introduction and video.
Give the microphone.
Can people hear me? Or?
Yes.
Yeah. For slide to like press.
Okay.
Slide.
This one.
This one. Okay, thank you. Today I'm going to tell you a story about conformal symmetry in nuclear reactions. The plan of my talk is to first review in very broad terms the notion of symmetries in physics, in particular quantary and conformal symmetry. For the later symmetry, the conformal symmetry, I'm going to describe a non-relativistic counterpart, non-relativistic conformal symmetry, and then argue that this symmetry is relevant for the physics of neutrons in a certain energy range, low energy. And then I'm going to tell you a story about something that we call UnNuclear Physics, for a reason that you're going to see. Symmetry plays a very big role in physics. In quantum mechanics, for example, we have a classification of states according to the rotational group SO3. And if the SO3 is a symmetry of the Hamiltonian, we know all the states are classified by a representation of the SO3 group. And this irreducible representation of the SO3 groups gives us the notion of spin. The spin is quantized in half integer for the reason that have to do with the mathematics of the representation of the SO3. We go to the Poincare symmetry, which is the symmetry of space-time, the relativistic space-time, and which consists of time and spatial translation, rotation, and Lorentz boost, altogether 10 generators. Then we have the notion of elementary particles as things that can be classified as unitary, non-reducible representation of Poincare group as Wigner told. In particular, if the mass of the particle is non-zero, then the state would be classified by the spin of the particles. And if the mass of the particle is zero, we know from the mathematics of the Poincare group and its representation that this particle can have helicity, which is the projection of the spin on the direction of motion. There is a symmetry that is larger than the Poincare symmetry, which is conformal symmetry and sometimes plays also some roles in physics. The conformal transformations are transformations that preserve the angles but not necessarily the length. In particular, so one example of such a transformation is dilatation or dilation, where we take all the coordinates and then expand by the same amount. See here that all the length has been dilated by the amount lambda, but all the right angle remains right angle. All the angles remain the same. But there are also other less trivial conformal transformations. So these are called proper conformal transformations that distort the space. So I'm trying to draw here an example in 2 dimensions where we have a transformation that changes the notion of length in a way that is not uniform in space, but all the angles remains the same. Or there is an infinite number of such transformations in 2 dimensions, but there are only a finite number of these transformations in dimension larger than 2. The field theory with these symmetries, conformal symmetries, are called conformal field theory, and they play some roles in physics, in particular in the physics of second-order phase transitions. The state of a system under second-order phase transition is thought to be invariant under conformal transformation, and it's described by a field theory with the symmetry called the conformal field theory. One may ask whether this conformal symmetry plays any role in particle physics, and the result which can be obtained right away by a very simple argument is that the standard model is not a conformal field theory. And the reason is the following: the conformal field theory cannot have massive particles with dispersion relation E equals square root of E squared plus M squared, where M is the mass of the particle. And that is because if we take the simple dilatation first transformation where all the space in time coordinates is expanded by the same, then energy and momentum we also have to transform by multiplication by the same amount, and this would disturb the validity of this equation. So conformal field theory cannot have massive particle. It can have massless particle. If M is equal to 0, E equal to M would still be valid after dilatation. Or it can have some things that are not more non-trivial than massless particles, some fuzzy stuff that I will try to describe later. So in a field theory, we are used to the notion of the propagator of the particle, which is 1 over p squared minus m squared, or I expanded to e squared minus m squared. That m squared is the thing that disturbs the scale invariance of the formal invariance of the theory. So if I have a propagator of a massless particle, it would be 1 over e squared minus p squared, which is a good propagator and object in conformal field theory. But it turned out that in conformal field theory there are more general objects. The propagator, which is not doesn't have a pole function of energy, but it can have a cut, so the propagator can have a form 1 over p squared minus e squared to some power, and that power doesn't have to be an integer. That power in conformal field theory is 2 minus delta, but delta is a quantity for the dimension of the operator. And if delta, 2 minus delta is not an integer, the propagator has a cut in the complex plane that as a function of energy, that starts from E equal to P and goes to the way to infinity. This would have a dramatic consequence. It's really describing some physics. So Georgia in 2007 made a proposal that maybe beyond standard model, we may have conformal field theories that couple very weakly to the particle in the standard model. Now, conformal field theory, as we've seen in the previous slide, has objects with which in some sense are the fuzzy object because they don't have a well-defined energy as a function of momentum. The cuts in the propagator of this object mean that if one fixes the momentum of this particle p, then the energy can be at any value starting from p times c to infinity. Georgia called this object an unparticle, and he imagined that this unparticle may be something that coupled to that it is beyond the standard model. So the signal of these unparticles, if they exist, would be a missing energy in the reaction between element and particle. So, for example, if we collide two particles, A1 and A2, it may create one particle and another object that is charged unparticle. If that U it was a particle, then from kinematics we know that if we fix the energy of A1 and A2, then the N in the center of mass frame, for example, then the energy of V and U will be completely determined by the conservation of energy. But if U is unparticle, that is, if U has doesn't have a fixed relationship between energy and momentum, then the spectrum of this particle V that can be detected, we assume it can be detected, and is continuous. So that would be signals of this unparticle. And the cross-section must have some peculiar dependence on the momentum energy carries by this U. If there is any question during my talk, please interrupt me at any time. So that is Georgia idea that if you collide some hadrons, a proton-proton collision, for example, then quark and an antiquark may fuse and give rise to left, for example, electron and some unparticle. And if one managed to measure all the energy of the final particles, one will be able to detect whether there is an unparticle that has been produced. And to summarize the experiments in one sentence, there's no one particle has been found in the LHC. There are some limits on whether what is the coupling constant of this unparticle to the particle in the standard model is limited by, but there is no detection from that. So in this talk, I'm now going to argue that the non-relativistic version of unparticle is actually realized, at least approximately, in nuclear physics, in nature. And that is the notion of UnNuclear Physics that I'm going to propose. This is a play of words upon Churchill's unparticle physics. These unnuclei are states that consist of a few neutrons. So very quickly about nuclear physics. A nucleus is a bound state, usually is a bound state of protons and neutrons, except for the nucleus of hydrogen, which is just one proton. All other nuclei all other atomic nuclei are made out of proton and neutrons. For example, deuterium would be one proton and one neutron, and helium-4 would be two protons, two neutrons. This is a triton, which is I mix up these two. This one is a triton, which is one proton and two neutrons. And this should be helium-3, which is two proton and one. Now one can ask whether there is in nature nuclei that made out of neutrons alone. One neutron would not be stable under weak interaction, and it is, but are there bound state of two neutron, three neutron, four, etc. Even when we turn off the weak interactions, most physicists believe that there is no multi-neutron bound state. There is no bound state that consists of few neutrons. But as I'm going to argue in these talks, it's still useful to think about the object that consists of a few neutrons as some kind of an unnuclear, non-relativistic version of Churchill's unparticle. Okay, so let's go to the history. The first article that I could find that made a remark that is very important for our talk is a paper by Zenrovich in 1960. So he was thinking about nuclei with very large number of neutrons, nuclei which we would now call nuclei near the edge of stability, and he predicted a few nuclei, for example, helium-8, that would be bound. But he also made a remark the remark is the following. The problem of the possibility of existence of heavy nuclei composed of neutrons or neutron only is considered. The problem is reduced to that of a Fermi gas with the resonance interaction between the particles. Then he made an argument that is very modern. That is the energy of the gas is proportional to omega to power 2/3 its omega density. As we will see, this one is actually Zendovic in 1960 already predicted the existence of physics of particle with resonance interaction, which now is realized in atoms with in an atomic track, or fermions with resonance interaction. So let's think about how this resonance interaction is realized in a very simple picture of quantum mechanics. So suppose we have two particles that interact with some attractive potential. So in undergrad quantum mechanics course, we will take the simplest potential, attractive potential of the shape of a well. The potential is minus V0 when the radius, the distance between two particles is less than some R0, and is zero outside. And one can solve the Schrödinger equations by standard method and find that if this V0, if the depth of the potential is larger than some critical value, which is written here as 1 over m, 1 over R0 squared, then there are bound states. Depending on how deep the potential is, you can have 1 bound state, 2 bound state, etc. But if the potential depth is smaller than that critical value, then there is no bound state. There is a critical value of P0 where there is a bound state. And let's imagine the following operation. We take the potential and tune the depth of the potential to be exactly at this value where there is just 1 bound state started to appear with zero energy. And then we shrink the size of the potential to zero. So first of all, what happens if the energy of the bound state is very small? That means the bound state wave function becomes very extended. The wave function outside the potential looks like e to minus r over 8 divided by r. And this a goes to infinity as we tune the depth of potential to the critical value. The bound state becomes larger and larger. And then let's imagine that at the same time as we fine-tune this potential to V0 depth, we shrink the size of the potential R0 to zero. So that limit, in that limit, the depth of the potential goes to infinity, but the size, the range of the interaction goes to zero. So that limit R0 goes to zero is called the unitarity limit. So it's very popular with people doing cold atom physics. They trap atoms and try to use some experimental technique to tune the interaction to this unitarity regime. This regime is called unitarity because the S-wave scattering amplitude saturates it. Any question about this? So this situation,
I guess I have a. Is this limit well defined? I mean, you're taking several limits at the same time.
Yeah.
Do they commute?
Do
we know that they commute?
We know experimentally that the limit exists and it's non-trivial. That is numerically. So this, I think the order of the limits should be taken as I described here. First, we will fix R0 and then take this equals to minus V0 and then tune R0 is zero. I'm not sure if there's another non-trivial. So this equation corresponds to a chapter in quantum mechanics textbook, for example, Landau Riches, low energy resonance scattering. You read the textbook, see that low energy resonance scattering are classified, can be parameterized by the scattering length, and we go further, it's the effective range of the interaction. And the unitarity regime corresponds to taking this scattering length to infinity and the effective range to 0. So there are two length scales, one goes to infinity, the other goes to 0. And in between, we have a physics with no dimension-full length scale. That means that the physics is scaling by. One can think more formally about this limit in the following way. One can think about this limit as a boundary condition of the wave function. Since the potential is now located at 0 distance when the two particles coincide, there is a one can formulate the problem in an equivalent fashion by imposing a boundary condition for the wave function. We have two particles with coordinate x and y. When they approach each other, usually in quantum mechanics, we would say that the wave function has to be regular, the two x goes to y. But in this particular regime, the wave function is x is 1 divided by x minus y. So the thing that is not really about function of 1 over x minus y is that if one apply the Laplacian on it, then we get 0 except at the point when x equal to 1. The 1 over x, 1 over r is a solution to the Laplace equation. So the boundary condition is that this wave function is to approach 1 over x minus y with some coefficient, and the remainder should be 0 when the coordinate of the two particles coincide. And one can show that the Hamiltonian, we take the Hamiltonian to be the Hamiltonian free particle, that it's a sum of the Laplacian. The Hamiltonian is Hermitian. It's very non-trivial thing to check. So now the unitarity regime is formulated as a problem where the Hamiltonian is trivial, but the Hilbert space is not trivial. Hilbert space composes a function that is singular like this.
So H for free particles is p squared over 2m.
P squared over 2m. Laplacian squared over 2m.
Okay, yeah.
So when you act on the wave function of that type, it remains of the same form.
That makes sense.
Yeah. So this system turned out to have an enhanced symmetry called the nonrelativistic conformal symmetry or Schrödinger symmetry. Okay, so what is this symmetry? So the Schrödinger equation in free space looks like this. And from one solution, when we construct many new ones, for example, I can rescale space and time and get a new solution. So I rescale space by lambda, time by lambda squared, because here the derivative with respect to time is first order, x is second order. So this is still a solution to the Schrödinger equation. So this operation also works for system of n particles in that previously called the unitarity regime. I can still rescale space by the same amount, and the boundary condition that we imposed in the previous slide is still be valid. But there are also another much more non-trivial transformation that one can make. And here I'm writing it for a function of one coordinate of one particle, but I can very easily extend it to a Schrödinger equation of minimal system. So this is how it looks like. X goes to x over 1 plus alpha t, t goes to t over 1 plus alpha t. Actually, I don't have a good reason. I don't have a good explanation why this would be a good transformation, but if one put that into the Schrödinger equation, one can see that we can generate a new solution to the Schrödinger equation by just changing the normalization of the wave function and the phase of the wave function by some factor. One can actually check directly that this one is still a new solution to the Schrödinger equation. So this is also a solution. That means that there is a very large group of symmetry that is satisfied by the Schrödinger equation, and people call that the Schrödinger symmetry. It consists of time and spatial translation, rotation in space, Galilean boost, where x goes to x minus bt. Scale transformation, c and x scaled by factor lambda square and lambda. And then this proper conformal transformation, the one that we have in this equations, and then the phase rotation. So all this got over the symmetry of the Schrödinger equation, and it formed a closed group called the Schrödinger group. And the algebra the algebra of this infinitesimal transformation is called Schrödinger algebra. So the algebra consists of the operator, the generators of the algebra are translation, Galilean boost, dilatation, proper conformal transformation, and there is a Hamiltonian also, translation in time. There is one more, I think I didn't write here, the mass or the total number of particles, which is a phase rotation, psi goes to psi plus IR, and it's computed everything. So here is a table of the commutator. You don't have to memorize it, except that I want to point out on some features of this algebra. Feature is immediate. Point down here. So this algebra contains the usual Galilean symmetry that has translation, boost, and translation in time. It has one element that commutative, that is the mass of the particle. And you can see that this D, C, and H also form a closed circle. Turn out to be a SO2,1. Okay, so now let's talk about system where this large scattering length is realized. In nature, there are a few systems where by accident we have a very large scattering band. One example is helium-4 atoms. Helium usually are thought of as inert gas that exists only in the atomic form. But if one goes to very low temperature, and one can see that two helium-4 atoms form a bound state, but that bound state is very weakly bound. The scattering length is 100 angstrom, which is at least 1.5 order of magnitude larger than the range of the interaction between the atoms of helium. Another example is neutrons. This example would be the one that is important for us. Neutrons do not form two body bound states. We have two neutrons together. The interaction is attractive, but not enough to form a bound state, but it's almost enough. The scattering length is pretty large, 20 Fermi. Minus sign here means that it does not have enough strength to form a bound state, but the scattering length is almost one order of magnitude larger than the effective range of the interaction. And as I mentioned, atom physicists now have managed to make a artificial system of ultracold trapped atoms when the scattering length can be tuned by a magnetic field using a method called the Feshbach resonance. So if one takes spin 1/2 fermions with its unitarity interaction, then this system is believed to possess nonrelativistic conformal symmetry, or this Schrödinger symmetry, for an arbitrary number of particles. Not just for 2 particles, but 3, 4, etc. It is known that this property would not be true for if we take bosons, spin 0 boson, 3 boson, although the system with 2 bosons would still have the symmetry, but 3 bosons start to have a phenomenon called the Efimov effect that breaks the non-relativistic components. So that means that neutrons will have approximate conformal symmetry, but this is only approximate and it's valid only in a certain energy range. And that energy range is fixed by the size of the scattering length, 20 Fermi, and the effective range, R0, which is about 3 Fermi. And this range is between 0.1 MeV in energy and 5 MeV. So if we have a system of neutrons, when the kinetic energy of the neutrons is between this range, then they have the system having proximate conformal symmetry. Any question? Okay, so now let me go a little bit into the formalism of non-relativistic conformal field theory. One can build up the formalism of a non-relativistic CFT in analogy with the relativistic theory. Many notions in usual CFT can be extended. For example, the notion of primary operator and the notion of operator dimension. So for this two operator with dimension delta, the two-point function of this operator has a scale invariant form, 1 divided by t to the power of delta times an exponent. And this is the form of the exponent is dictated by Galilean by cx squared t. And the form here is fixed by form symmetry. Some examples of dimension of operators. So, elementary field in non-relativistic field theory of free bosonic field or fermionic field have dimension 3.5. So this would mean that its dimension is it has the same its dimension as momentum to the power of 3.5. In free field theory, you can take two fermions with spin up and spin down, for example, you can multiply them, and the dimension of this operator would be equal to 3. But in the theory of unitarity fermions, turn out that this operator does not exist anymore. The reason is the following. We have to construct another operator that have a finite matrix element between the state which has two particles in the vacuum. This operator psi is an operator that annihilates two particles, right? And this operator in the theory of unitarity fermion has to be defined so that the matrix elements is equal to psi xy times x minus y in the limit x goes to 1. Normally in quantum mechanics in the second quantized formalism, we would define this operator to have no to this operator, the matrix element would be the value of the wave function in 2.1 and that is infinite when the fermions are at unitarity by the non-trivial boundary condition. So the conclusion is that an operator that exists in the theory of non-unitarity fermion is another operator which has dimension 2 instead of 3. That's the consequence of the non-trivial boundary condition. So this led us to the notion of an unnucleus. If we think about this operator, side down, side up, as an operator that annihilates a certain object, that object, I will call that object an unnucleus. It's not a bound state. It doesn't, when I compute the correlation function, it doesn't have a pole. So it's an operator in a non-relativistic conformal field. One can characterize it by quantum number. For example, the spin is 0, orbital angular momentum is 0, the mass of this object is 2m, but the spin dimension of this object is 2. Which means that it's not an elementary particle, it's not a particle with dimension have to be 3.5. It's not a superposition of two particles, dimension has to be 3, but it's an operator with dimension 2. And the correlation function of this object is 1 over t squared. And one can also extend this notion to more complicated objects. Now, the 3 particles or 4 particles, one can put these 3 operators side up, side down, for example, that would have spin 1/2. And we can consider them in different angular momentum channel. And here I'm not going to explain how to compute the dimension of this operator. We can solve some, we can use quantum field theory or some analogous quantum mechanical system, but it turned out that the dimension of the operators that create these objects are now non-trivial. This number 4.273, in practice, it's known to exactly the solution to some transcendental trigonometric equations. But for 4 particles, the numbers start to be computable only numerically. For example, the dimension here is known not very well.
Sorry, but I mean, physically, these nuclei would be neutrons if their binding energy was in the unitary limit.
There is no, it's not bound. So this object would be not bound.
Yeah. But it's like neutrons if their interaction was close to
Suppose we have particle with exact neutron is only approximate particle with approximate unitarity limit. Imagine that they are in the unitarity limit. Then I can ask the question: what is the operator that creates this object? This conformal.
So basically, like with ultracold atoms, you could try to create these things.
They would be they would not create. Well, in experiment, what happens is quantum experiment and this object actually disappear. The 3 particle comes in and they disappear by a process of loss. So the process of losing particle from the atomic trap are actually dictated by this exponent. So in Cal4 atoms, these are things that actually happen. Okay, so the this, let me see if I get the slide. So let me explain this slide a little better. So it turns out that this dimension can be understood, can be mapped through an operation called operator state correspondent. And the nature of this correspondent is the following. In order to turn out that the dimension of an operator is equal to the energy of a system of particles in a harmonic trap with some fixed potential, fixed frequency omega. So for example, if I put 2 particles, this spin up and spin down, in a harmonic potential, I know exactly what is the ground state energy if the interaction between them is unitary. I know the exact wave function, and the energy is equal to 2 at h bar. Now, if the particles do not interact with each other, the energy will be 3, because each of particle has energy 3½ h bar omega in 3 dimension potential. But the interaction, the attractive interaction between particles uses to number 2, is number to 2. So one can put in one more particle, spin up, for example, and get this number. These numbers are the 2 lowest energy eigenstate of a system of 3 particles in harmonic potential with interaction functioning unitarity. And this is also the energy of 4 particles unitarity interaction in harmonic potential. Okay, so now let me describe to you a non-relativistic version of unparticle physics. Non-relativistic called UnNuclear Physics. So this is based on a paper that I wrote with Hans Hammer in 2001. Let's consider a nuclear reaction where the final state consists of a single particle and a few neutrons. So some examples, actually we are not going to use this example later on, but some of these are, for example, this is a reaction with 2 neutrons, 3 or 4 neutrons. So let's think about this reaction as something that occurs in 2 steps. In the first step, the 2 particles come in, react, and create a particle V and an unnucleus U. And in the second step, this unnucleus U decays into, in this case, 3 particles. When this factorization is supposed to happen, that is when the energy scale of the primary reaction is very large compared to the energy scale of the decay. Then the first primary reaction would be instantaneous. Then it creates a nucleus, and then it is fly out to a distance, for example, comparable to 20 Fermi, and then decay to one nucleus. So if this, there is a separation of energy scale, then the probability of this reaction can be decomposed into the product. These two probabilities. So now let's imagine if that is happened, if that is the case, then one can do a very simple analysis and figure out the following scaling up. And you can draw another picture on the board. Here I'm trying to understand the differential cross-section as a function of the energy of this particle B, which is, I call this E here. Now this energy of B is continuous, it has a continuous spectrum, and it has a minimum. That's the maximum value. If we look at this vicinity of E0, we see exactly the type of separation of energy scale. All these particles, all the neutron with E is very close to zero. The particle B carries a lot of energy, All the neutron has to go in the same direction, almost with the same velocity. And doing kinematics, we can show that all these neutrons will have very low energy with respect to each other. So they may have a large energy with respect to the frame of particles holding the lab frame, but in their own center of mass frame, they have small energy. And the differential cross-section can be then computed by multiplying the energy of this, the scattering amplitude of the primary reaction with the imaginary part of the propagator of this unparticled B. Okay. So what we have used here, we have used this factorization formula, and the fact that the probability of decay is the imaginary part of the propagator of U. Now U is unparticularized, has the imaginary part is a scaling behavior, and that means that we can now rewrite this together with this imaginary part is E naught minus E by kinematics. The energy of the neutrons in its center of mass frame is E naught minus E to the power delta minus phi naught. So near the endpoint of this graph, the behavior here is dictated by conformal symmetry. It is here E to the power delta minus. And delta is the dimension of the operator that create this unparticle. So let's look at the numbers. So in the processes where we have two neutrons emitted in the final state, this power alpha is minus 0.5. That means that the differential cross section is enhanced near the endpoint by the interaction between the particles. This behavior actually is known for a very long time. Migdal and Watson derived this behavior, this exponents in late 1950s. For the reaction with the emission of 3 or 4 neutrons, we find the behavior that the differential cross section is close to 0, but with exponents that are non-trivial. 1.77, one case, and for 4 particles will be around 2.5. The regime of validity of this behavior is when the kinetic energy of the neutrons between 0.1 MeV and 5 MeV. So that is a regime that is, usually this energy is considered small in nuclear physics. So usually this behavior occurs in a certain corner in the kinematics of the reaction. One of such reactions is the reaction when triton reaction with pi minus. So that Triton is a bound state of proton and two neutrons. It can form with the ionic atoms. So if you take these ionic atoms and wait a little bit, this ion at some point can be absorbed by the nucleus. And normally what happens is that the ion state has 3 neutrons, but sometimes a gamma particle is also emitted. This kind of reaction has attracted attention in experimentalists. In the past, when we were trying to find out if there are bound states of 3 neutrons, they couldn't find bound state of 3 neutrons. But experimental data exists for the differential cross section when the energy here is energy of a gamma particle. So here I'm plotting the graph that is not the graph of the experimental result, but of a theoretical calculation, which has a larger accuracy near the endpoint. And I plot the differential cross section as a function of the energy of 3 neutrons in the final states in their own center of mass rate. So this E3m is related to the energy of the photon. And here the experimental point, sorry, the theoretical point, theoretically here, but this is using a model that's supposed to capture nuclear physics very accurately with the output potential of 40 parameters and with the good modeling of the reaction of ion with the proton. This point, pseudo experimental point, seems to lie very well on the curve, on the simplest curve. That is the exponent to about 177.
So this is all theory, there is no experiment?
Yeah, yes, the experiment, experimental result doesn't have enough, and we try to look at that, doesn't have enough accuracy near the end point. So we, at this moment, we couldn't compare the prediction with the real experiment. So I have to compare it with some theory, but
Numeric.
Numerics, but supposedly it's a good model with all the ingredients of nuclear physics. Maybe more than enough, because they are all this very detailed treatment of proton-neutron and interneutron interaction.
So what makes CFP work is the fact that the neutrons are nearly collinear.
Nearly collinear, yeah. Nearly collinear, and it's we couldn't see. So the theory predicts that we go right here. This should be diverged from here, but 0.1 is very small, so we don't have enough. We don't have any data that these people produce in data narration. So here another thing is that it diverges from the theory starting around 2.5. The naive estimate is 5 MeV, but it's according to, so it's still probably could be 9. Maybe the hybrid Triton is not the best source of this neutron. In the factorization procedure, factorization works best if the source of the neutrons is a point-like source. And the Triton is somewhat of an object that is not very tightly bound. Binding energy is only about 2.5, about 3 MeV, 2.5, 3 MeV per power. So maybe that explains the deviation. But in between this, it seems that there is a scaling law that is satisfied very well. Now, this point, let me explain also this point. This point is not experimental point. This point is produced by the same author by turning off the final state interaction between the neutrons. So they assume that once this neutron are produced, they do not interact with each other. And they produce this point. This point lies on the curve which has the exponent equal to 3. And that exponent is also very well, we can understand it. It's related to the dimension of the operator that produces 3 neutrons in free field theory. In the theory of neutrons, free. And so when neutrons are free, the first operator with 3 neutrons are psi up, psi down. You want to put a psi up here, but there is no way to put aside without derivative because they are fermion. So the dimension of this operator is 11/2 minus 5/2. That is 3. That is to the power of 3. So the microscopic model gives us both this curve of the unitarity fermions and the free fermion. And they also, in the paper, they also look at the reaction of capture of muons emitting a muonic neutrino. And imagine that one can measure the energy of the muonic neutrino, which I think is a very difficult thing to do, but in this, if one can do that, then one should be able also to see the same exponent in a slightly different reaction. Okay, so that's the conclusion of my talk. There is a non-relativistic version of conformal field theory. And the example is fermion unitarity. It's the best understood non-relativistic conformal field theory, and it is also relevant in physics because it's approximately realized by neutrons, and it's linked to UnNuclear. That is power law behavior of the differential cross-section of several processes near the threshold. And here we have considered just one process, but presumably there are many other reactions where one should be able to see that behavior. One can zoom in the appropriate regime, and one can speculate that this physics might be also possible to study in Cold scale. One can do scattering through the Cold. Thank you very much.
Perguntas? Questions? I have a question. In the beginning you said that you can think of this as being a free particle Hamiltonian and boundary condition of a wave function. In path integrals, can one translate this into a topological term and a sort of boundary condition on the configuration space?
There are two versions of path integral. So one quantum mechanical integral when the particle follows certain trajectory.
Exactly. Yeah. Can you show the boundary condition on the slide? How does it translate to path integral?
Path integral in a way that
yeah, this one.
yeah, so you have two particles. Actually, it's actually an interesting question. I don't know the answer to this question. There's one example where one should be able to do this is something called alien. So alien has a boundary condition that is slightly different. Alien boundary condition is that when you take one particle around the other, the wave function changes their phase. It's also scaling variant, so it's the 2 plus 1 dimensional theory of alien is also conformal. In that case, I know how to suppose that we know how to do path integral. We just set about all this path and then assign the very different phases to different Miley number of particles around. So this one actually is interesting, but
Because if it's a free particle, the Hamiltonian and the Lagrangian are the same, right?
Right. Yeah.
But the boundary, you have to think of topological.
It's and one can think about having the two trajectory intersect one point and then diverges further, and presumably there's one have to put in some weight or something.
Does this function does it satisfy the Schrödinger equation? Because when you apply the Laplacian, there is a direct delta function.
Yes, so we assume, so the rule here is that when you apply the Hamiltonian, it's supposed to throw away this delta function. So the delta function has to be thrown away. Then the Hamiltonian, with this procedure, the Hamiltonian is Hermitian.
We just throw in
The delta function.
But this is like the conformal limit. Is this part of the conformal limit that you throw away the delta function?
Functions not related to the definition of this operator.
Can you somehow, in the conformal theory, get these extended group that you showed
From the relativistic conformal field theory, we can obtain it by procedure of line reduction. That is, in the conformal algebra, there are operator of momentum as part of the conformal algebra. So let's take one line momentum, PV, example, and then select all the operators that commute, which is T plus. In the algebra, they form a closed algebra because of the mutual Jacobi identity. And these are the non-relativistic conformal symmetry in one less space-time dimension. So,
is there some interpretation of that property of the name, that it's a mixture of the scale and phasing?
what is this map? I have it written in the paper, but I have to. But one can map all these operators to operate. So I forget what it is. Actually, there is various things that one can guess. So there is a m plus minus. It's a one elements of the Lorentz group. There is a dilatation. I'm not sure if the linear combination of these two or something. I think the linear combination of these two becomes a dilatation in the non-relativistic theory. Okay, but C is proper. I can look that. I can look after the talk.
I mean, about the relativistic limit of this, let's go back to relativistic. You have this scaling laws for, since you have these scaling laws for neutrons, if you have jet fragmentation, it works in gluons. Do they follow something similar to a certain approximation? In the various, big lap and BFK, gluons and quarks are also basically massless objects which interact with each other, and you have a limit of momentum. I mean, the limit of momentum goes to zero, of course, confinement. But let's say that you have what now they call saturation. You have this asymptotic regime, the asymptotic BFKL regime or something like that. Do we know that if fragmentation into n gluons follow scaling laws of the type as decay into n neutrons?
Yeah, I don't know this fragmentation well enough to say what the simplest version of this of the Georgia particle is just 3 particles. So phase space of n particles looks like Georgia particle with some integer dimension. Dimension is the number of this particle. When the interactions on the linear interaction equation, with the running, well, I suspect the behavior is much more complicated because there is no scale invariance. No,
Well, approximately you have scale invariance.
it's alpha doesn't. If that alpha doesn't run fast, then
You are in the asymptotic dynamic here.
yeah, sometimes these things sum up to an exponent. And they might have a relation. So that I mentioned.
Yes. If not, thank you very much.